Hey guys, my name is Rahika Nandi and I'm a student in CHEM 6BL and my TA is Nick Davis. So today we're going to be doing a lab about pH using purple cabbage as a pH indicator. So to begin, the ingredients that we are going to need are purple cabbage, glass beakers, and because I don't have beakers, we're going to be using glass cups or glasses. This will be in order to test the pH of different substances. We'll also need a chopping board and a knife to cut the cabbage, a water boiler that is used to have the cabbage become water soluble when we boil it, and also the different substances that we are going to use to test the pH. We will be cutting the cabbage that will be used, and simultaneously over there we will be boiling some water in the water boiler, and that will be used with the cabbage. So the reason that we boil the cabbage is because the cabbage has a pigment called anthocyanin that resides in the cabbage itself, making it the color that it is. Anthocyanins are water-soluble vacuolar pigments which turn red in acidic conditions where the pH is less than 7 and turn blue-green in basic conditions where the pH is greater than 7. So, for example, blackberries, blueberries, cherries, cranberries, and in addition to purple cabbage are all owners of these pigments. Boiling with water is going to aid in extracting the anthocyanin due to its water-soluble nature. So this here is a structure of anthocyanin and what is found in our lab due to the fact that we are using purple cabbage. The next step of our experiment is to basically, once the water is completely boiled, then pour it into our beakers. After, we'll quickly put the cut cabbage into the beakers in order to soak for approximately 10 to 15 minutes. The reason the lab will work is due to the stability of the anthocyanins. So we are going to see in the results how the colors are able to properly change when the pH indicator is used against different substances with known pH differences. Anthocyanin stability is dependent on the B ring in the structure in addition to the presence of a hydroxyl or methoxyl group. These groups decrease the stability of anthocyanin in the solution. As anthocyanins have an ionic nature, the color changes are purely dependent on the pH of the solution, and because of this, there's going to be a different pH dependent on how the anthocyanins is destabilized. So, as said before, in acidic conditions, the color of the water will be red. In basic conditions, the color of the water will be blue or green, and in neutral conditions, the water will be purple, just like the color of the cabbage itself. To explain further, the red color pigments in the anthocyanin originate in flavulum cations. These flavulum cations have increased stability at a lower pH and therefore enable anthocyanin to be more soluble in water, showing the red colors most predominantly. An additional factor to this in this experiment must be specified is the water concentration level. A decreased water concentration will increase the rate of deprotonation of the flavulum cations, and so this essentially reduces the color stability for it to become more red and therefore must be accounted for. A more basic condition causes degradation of the high stability that anthocyanin pigments have in the acidic conditions. Additionally, anthocyanin loses an OH at acidic pHs but gains an OH group at basic pHs. So generally, we already know that an acidic solution has extra protons, or H+, while a basic solution has less free H+ protons. So by this knowledge, we can explain how the structural changes cause physical pH difference in the solution more than just the color change itself. Next step in the procedure is that after boiling the water with the purple cabbage for approximately 10 to 15 minutes and straining out the cabbage, we can then observe and record the color of the water in all three beakers. This here represents our neutral and our starting material. So basically it's what originally comes from the cabbage itself. set aside one beaker as a control to show that the original color of the cabbage pH indicator is without being in a solution in comparison to the other cups and glasses once we mix in the substances. We will be using lemon juice to create our acidic conditions and laundry detergent to represent our basic conditions. To do the experiment, we will just mix our acidic and basic substances into their respective beakers and observe the color change. First, as the lemon juice is added and mixed, we can see how the colors change compared to the control beaker with the starting material, becoming more red-pink to represent the acidic condition. Similarly, when the detergent is added, the color changes, but it's different and it becomes more blue or green, representing a basic condition. The acidic lemon juice and the color change towards the red and pink color, while the basic detergent and the color change towards a more blue-green color, proves that purple cabbage is a good pH indicator for the final products and therefore any substances. I hope you enjoyed this quick little experiment and explanation, and hopefully you learned a little bit more about pH indicators and how structure is definitely important with respect to determining whether it will be a good pH indicator or not, and that anthocyanins are really good pH indicators. So, thank you so much for joining me.